So we want to look at what's called RSA cryptography. RSA cryptography. RSA cryptographic system. Or RSA cryptography. So I don't know if you are aware of this, but militaries, modern militaries, and modern intelligence agencies are very much concerned with cryptography. They want to be able to send messages without their adversaries being aware of what they're communicating about. So militaries do this, CIA does this, they're heavily involved in cryptography, and also a big one is called the NSA, That's the National Security Administration. So this is probably the biggest employer of cryptographers in the world. So they are part of the U.S. federal government. They're an agency, one of the alphabet agencies, NSA, that is primarily concerned with cryptography. They hire a lot of mathematicians and computer scientists. So if you get a job, you might try applying for a job there. If you study mathematics or computer science, you can apply there for a job, and they pay pretty well. They're located near Washington, D.C., in what's called Fort Meade, Maryland. Fort Meade, Maryland is their headquarters. But in order to get a job there, you have to go through a lot of different background checks and, that kind of thing. They make you take a lie detector test, a polygraph. They're very, you have to have what's called a security clearance. And you can't share your job with other people. Well, and anyway, so we're talking about sending codes so that other people so adversaries cannot discover what you're communicating about. And one that was developed in the 1900s, or the 20th century as we would now call it, that's pretty much unbreakable. You can't break the code very efficiently. It's called the RSA cryptographic system. It's named after three guys from MIT, Rivest, Shamir, and Adelman. And these are three MIT guys. These guys are from MIT. And I believe it was around 1977 that they published their work, their discovery of RSA. But in reality, this was actually discovered much earlier. Well, not much earlier, a few years earlier. I believe Clifford Cox discovered this independently. So Clifford Cox, he was part of GCHQ, which is British intelligence. He worked for British intelligence. And as a British intelligence agent, he developed this method on his own before Rivest, Shamir, and Adelman. So this was 1973 that he developed it. Now, it was classified for many years. For many years, it was classified. So these other guys from MIT had no idea that Clifford Cox had discovered it himself. So they thought they were the ones that discovered it, but in reality it was classified. And I think until probably the 1990s, the British Intelligence Agency declassified it. And then we said, oh, so this guy actually discovered it first, before R, S, and A. In any case, RS and A, they get the credit primarily because their name is affixed to it, right? RSA. So it was actually two groups that discovered it. This group from MIT, which they made it public right away as soon as they discovered it, and this other British intelligence agency that had been using it. So there are probably lots of other cryptographic systems that we don't know about that are really high level. like RSA, and we just don't know about them because maybe the NSA or the CIA use them, and they're not going to release those methods because they don't want their adversaries knowing about these methods. But in any case, we want to talk about how RSA works. So the idea is you have a computer, which we'll call the host. And you have lots of other computers. Which we call the users. And the host gives out a public key. So his computer communicates with the other computers. Everyone gets what's called a public key. And everyone, let's say, has the same public key. So the users can encrypt. They can encrypt with the public key and send everything, their information to the host. So here we have encryption. Encryption with the public key. So the users encrypt their data, their information, send it to the host. And the host has a private key that only he knows. And no one can figure out the private key. So even though all the others have the same public key, they can't figure out the private key. It's just too difficult for them to figure it out. Too difficult. So only the host can decode. So this is the idea behind RSA, and we want to actually go step by step exactly what happens. So number one, the host with his computer randomly generates two enormous primes. So enormous primes. These are primes that are so big they have maybe possibly millions of digits or even more digits, maybe billions of digits. These primes are going to be called P and Q. So his computer generates these two primes. Number two, the host computer calculates the product of those primes, which we're going to call n. So he's going to take the p times the q together, and we're going to get this ginormous number. N is going to be this ginormous number. These two ginormous primes multiplied together to get a ginormous number. Number three, the host computer randomly generates an integer, which we're going to call d. This is the private key. This is called the private key. And this private key, D, has to have a special property. It has to have the property that, first of all, this positive integer D has to be greater than 1 and less than P minus 1 times Q minus 1. So you take those primes, subtract 1 from them, multiply them together. So that's an upper bound for the D. And also, the greatest common divisor of D and the product of P minus 1 with Q minus 1 has to be 1. So D and P minus 1 times Q minus 1 are relatively prime. There are no primes in common between D, P minus 1, and Q minus 1. So that's how the D is randomly selected. It's randomly selected that way with the computer. So that's the private key. So D is the private key. So number 4, the host then calculates the inverse of D, mod P minus 1, Q minus 1. He's going to call that E. So he calculates E, which is D minus 1. The inverse of D, mod P minus 1 times Q minus 1. So this E here, this is sometimes called the public key exponent. This is the public key exponent. And he sends this E together with the modulus N as the public key. So step 5, the host sends the public key. It consists of two things, E, the public key exponent, and N, the public key modulus, to users. So E is the public key exponent, and N is the public key modulus. And number 6, so all of the users will now have the public key. And they're going to use the public key, E comma N, to encrypt the data. So I'm going to say users use public key to encrypt data. So the encryption function, here's the encryption function using the public key. So the code is going to be congruent to the message. So the public key exponent is going to be E. So we have M to the E, and we're going to be mod N. That's the public key modulus. So that's the encryption function. So the E is the exponent, the N is the modulus in the public key. All right, then we're going to do a number 7. So we just said that the users are using this public key to encrypt their data. So they send their data to the host, and then the host uses the private key, which we're going to call D, right? We found D earlier. So D is the inverse of E. So he already has the private key. He's already generated it. So D is the inverse of E, mod P minus 1, Q minus 1. So we already proclaimed, so he already has it. The host already has the private key. And he's going to use that to decrypt the data. Can I get this direct? To decrypt data sent by users. So his decryption function then the message is going to be congruent to the code raised to the D power, mod N. So basically, the private key D is the decryption exponent. Okay, so what do you really need to know here? You need to know that things to know. One, you need to know the encryption function. Given the public key, E comma N. So the encryption function we said was what? C is congruent to M raised to the E power mod N. You need to know that. 2, you need to know how to find the decryption or the private key, the decryption key or the private key. Private key is called D. So D is E inverse mod P minus 1 minus Q, or times Q minus 1. E inverse mod P minus 1, Q minus 1. What are P and Q? Well, P and Q, remember what P and Q are. P and Q are the two primes that make up N. And number 3, once you have the private key, you want to know how to get the decryption function. Given the private key. D. And that is, the message is congruent to the code to the dth power, modulo n. Yeah. So that is what you basically need to know for the theoretical side of RSA. And what we'll do in the next video, we'll work through some encryption.